Ions are atoms or groups of atoms that have gained or lost electrons. Positive charge gained or lost electrons. Electrons have a negative charge. So if we lose electrons, we now have a positive charge. There are more positive protons than there are negative electrons. These positive charged atoms are called cations. Whenever I first learned this one, I was told that it's positive because if someone hates cats, they are positive they hate cats. You cannot change their mind. A negatively charged atom is called an anion. These can occur whenever an atom gains electrons. Electrons have that negative charge, so once we have, say, 8 protons and 9 electrons, we're going to have an overall negative charge in our atom. Now, these ions are very important in the body because they help provide what's been called bioelectricity. This positive and negative charge, when we gather them up together, they can provide part of what allows the action potential to They can allow for your thoughts to happen using that action potential across the membrane. We'll learn more about that in the nervous system. A good example of an ion is a potassium ion. This one has a positive charge, making it a cation. Calcium ion also has a positive charge. In this case, it appears that it has gained. In this case, you'll see it's 2+. That just means that we actually have 2 positive charges, so we must have lost 2 electrons. A sodium ion also has that positive charge. But who has a negative charge? Chloride. Chloride ions are negatively charged. That means they're anions. Now these guys, we're going to see them again in muscles. We're going to see them in the nervous system. We're going to see them with our bones. They're very important for all of those systems. And most of these are minor elements, but essential. Let's see how these atoms are binding together. When we have 2 ions, a positively charged cation and a negatively charged anion, these are going to be able to bond very well together because they're positive and negative. An example of an ionic compound is table salt. It's a combination of sodium with a positive charge and chloride with a negative charge. These two things come together and form table salt. Here's an example. Over here, we have our sodium atom. Now, sodium atoms have 11 protons inside of the nucleus, and to balance that, 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This gives us a nice neutral charge for our atom. Chlorine, on the other hand, has 17 protons, so it should have 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That gives it an overall neutral charge. What is happening here in ionic bonding is that this little guy is on the outermost ring and he has no pair. You'll notice the electrons like to be paired together. This little guy is all alone on the outer ring. And that's a position where he's not very stable in that position. So if chlorine comes along and has that outer ring, it wants to go, and it's actually going to leave the atom of sodium and travel over to the ring for the chlorine. Now when this happens, your sodium becomes positive because it lost an electron, and your chloride became negative because it gained an electron. But they are happy to do that because look at how nice and stable their outer ring is now. On both of them, they're completely full. They have all 8 electrons in their outer ring, and they're very stable. So these guys like to lose that electron and to gain that electron. And when they do, they can combine into a lattice crystal of table salt. A different type of bond is called the covalent bond. This is a connection between atoms based on sharing the electrons instead of, like in our previous example, the taking of an electron. The chlorine took the sodium's electron, balancing out their outer circles. But here they don't take, they share. Now in nonpolar covalent bonds, the sharing is equal. This happens when a hydrogen and a hydrogen meet. Hydrogens each have only 1 electron, so remember they like to pair up and have buddies. So when they're alone on that outer ring, they're all by themselves. So when 2 hydrogens get close enough together, those electrons love to pair up. And when they do, the hydrogens are going to share their electrons so that each of them have an outer ring that's full. Because they're sharing, they don't have a positive or a negative charge. They're still neutral. They each have 1 proton, so a positive charge and a positive charge, and they're surrounded by 2 negative charges. So they're still neutral. We call this a nonpolar bond because the hydrogen electrons do not spend more time with one hydrogen than the other, so the charge is going to be balanced across the molecule. A polar covalent bond forms when oxygen and hydrogens combine, but the sharing is not as equal as it was. If you've ever seen a playground and one really big kid is sharing with 2 little kids, who do you think can have the toy most of the time? They're still sharing, but there's a good chance that bigger kid's gonna be holding it most of the time. And this is the same thing. Oxygen is much bigger than the little hydrogens. Now, this oxygen would normally have 8 electrons, but after it shares with the hydrogens, it brings its grand total up to 10. This is a very stable, happy number for this oxygen. But as you can imagine, the majority of the time, those little electrons are hanging out on the oxygen side. So the hydrogens, they're sharing, but the majority of the time, they don't have those electrons. Electrons have a negative charge. So whenever the oxygen is kind of hogging them, it's going to give the oxygen side of the molecule a partial negative charge, and the hydrogen sides a partial positive. This is just enough to make the molecule polar. It means that there's a negative side and a positive side. It's not to a full ion, but we are sharing still. We did not take the hydrogen's electrons, but that sharing is unequal enough that it makes it positive-ended and negative-ended. Now this small detail, the partial positive and the partial negative, is pretty amazing. Without it, you would not exist right now. This molecule is called H2O. It has 2 hydrogens and 1 oxygen, and it can make up to 2/3 of the human body. This is a polar molecule, like we just said, and the delta plus and the delta minus represent that small charge generated across the bond. Because of that polar charge, water is a universal solvent. This means that most substances dissolve in it. Over the next few slides, we're going to look at how substances dissolve. The next slide includes a couple of terms, and then we'll see it in action. A solvent is a liquid that substances can dissolve in. A solvent is a liquid that substances can dissolve in. Water would be an example. A solute is a substance which is dissolved. If we added table salt to water, table salt would be the solute and the solvent would be the water. When we say dissolve, it means that the molecules remain intact, but they disperse in the liquid solvent. Substances that dissolve in water are called hydrophilic, means water-loving. Typically, this is going to be the polar molecules. Hydrophobic substances are water-fearing, and these they will not dissolve into water. Dissociate is when molecules pull apart into their individual components. Phew, this is a busy slide. We're going to start by looking at the left box here that says hydrophilic substances dissolve in water. Water-loving substances, these are going to be the polar ones. For our picture, we have a glass beaker full of water, and in that we are going to put a big block of glucose. This is going to be sugar. The glucose is going to go into the water and it's going to dissolve. If you taste this water, it is sweet, but if you look at it, it would still look clear because you've mixed that glucose in. Every glucose molecule remains intact. They're all just dispersed in the water. In our second example, we are going to take regular table salt. We're going to add that to a beaker of water. Since table salt is composed of charged ions, those are actually going to be pulled apart by the polar bonds of the water. So they dissociate into sodium and chlorine. Then we have hydrophobic substances that do not dissolve in water. Water-fearing substances, these are going to be nonpolar. Because they are nonpolar and they don't have a positive or negative charge, they're actually repelled by the polarity of the water. They don't want to be around it, and naturally they're going to be stuck onto that surface normally on the outside as far from the water molecules as they can get. They're being excluded or pushed away by that water. You've seen this yourself if you've ever tried to mix oil and water. They refuse. You can stir or blend as much as you want, but after it settles, all of that oil is going to rise up to the surface and form a big glob. It's being pushed away by the water. This curiosity that nonpolar substances are pushed away by water is actually one of the main reasons that you have cells and that you're able to exist and function. Inside of the body, we need to separate some liquids from others. We may need different concentrations of ions inside of them. We may need to trap organelles or nutrients inside of things. So to do that, we are going to create a membrane called a bilipid membrane that consists of polar heads that like the water and face it, and nonpolar tails that really dislike the water. Because they are hydrophobic, they will actually form a little membrane inside that does not want the water molecules to come in. It creates a barrier. The barrier this creates forms the walls of your cells and is essential to life. The barriers this creates is actually essential to life. All right, you made it through the heaviest chemistry section.